Now, any questions on this? Now, let's see. This is just a hollow tube, if you would like to look through. And if you just, well, this is something that can go through a metal. It once goes through. Well, this looks almost identical. Now let's see how it works. Now this is our long tube. It's a conductor. It's aluminum. It's non-magnetic. It doesn't affect from a magnet. It's not attracted or repelled from a magnet. But it's a conductor. And then you put a magnet in it. Let's say this is the North Pole, this is the South Pole. And it will have magnetic field lines that look like this. It starts from the North Pole, goes to the South Pole. Now let me imagine a ring right over here. So what will be the magnet is moving downwards. Now what will be the direction of the induced current over on that ring? Well, let's see. The magnetic fields look kind of upward. They go up. Close to the ring, they go upwards. Okay? So as it is approaching, the intensity is increasing. So if you choose the direction of the area to be upward, the flux is increasing in the upward direction. So the induced current will be such that it should create an additional flux pointing downward, trying to decrease. So it should be rotating, at least at the edge closer to you, it is going from right to left. So this will be the direction of the induced current. You see, this current itself will behave like a magnet. What is the direction of, in which direction is the North Pole of this magnet? North Pole is down, the South Pole is up. So here we have two South Poles. So this loop will push this magnet upward. Again, consistent with Lenz's rule. What does Lenz's rule tells us? Well, that current is created due to the downward motion of that magnet. So the induced current will be such that it will oppose it. It will push it upward. Now, for example, in this case, it keeps on, at the beginning, the velocity is almost zero. So there is no current created. So there is no induced force. Then it starts accelerating. The faster it gets, the larger currents it will induce. Eventually, there will come a point when the forces created by all these currents here and all the currents above will balance the weight of the object, and then it just keeps on moving with constant speed. There's the initial acceleration, then it will just move with constant speed. Well, let's look at the loop at the top of that magnet. Let's look at this ring, this loop at the top. What will be the direction of that in this current over there? Hmm? Well, let's see. You see, the magnetic field line is more or less pointing upward. So if I choose the area vector to be upward, the flux is positive. And it is decreasing because the magnet is going away. The magnitude of B is decreasing. So we have a positive flux which is decreasing. So the induced current should be such that it tries to increase the flux. But that means it should create a magnetic field in the upward direction, for which the current should be in the opposite direction to the lower one. So that for this small magnet, for this region, it just acts as if this is the North Pole, this is the South Pole. The currents at the top will be pulling the magnet upward. The currents at the bottom will be pushing it upward. All of them will try to prevent the motion of the magnet. So that's why the acceleration decreases and then eventually stops. Well, you see, what this does is it slows down the magnet. It doesn't stop the magnet. It just slows it down. You see, initially when I release the magnet, it has zero velocity, so there are no induced charges, no induced currents. But then that magnet accelerates, starts to move downward. Well, you see, the rate of change, the rate of change of flux is proportional to the speed. Well, the larger the speed, the larger the induced EMF, and hence the larger the current running on the surface of the tube. But if this happens, but these currents will try to push the ring upward. Well, as the magnet is accelerating, the currents will get larger and larger until the weight is balanced by the gravitation, by the magnetic push. But once they are balanced, that means there is no force acting on the magnet, so it will just move with constant velocity. It will not stop. Now let's look at a solenoid. You see, we have always been saying that, okay, let's assume a space where the magnetic field is uniform, let's change the magnetic field, etc. But how do we create them? Essentially through a solenoid, because we had already seen that in a solenoid, inside the magnetic field is uniform and the magnetic field is proportional to the current running through the system. So if you change the current, you change the magnetic field. So let's say that we have a solenoid such that there is a current running in the counterclockwise sense. And so the magnetic field is in which direction? It's pointing towards you, out of the screen. Do you remember what was the magnetic field created by the solenoid? n times I times, well, there's also the mu 0. Mu 0 and I. So if you change I, you are changing the magnetic field. So let's say that you change the current. So, but changing the current means that you are creating an EMF. Well, in this problem, there's no loop. There's no wire that will carry the current, but still, that changing the EMF, you can create the EMF even if you are not moving any charges around. The EMF is there, and the EMF will be E dot dl. So this will still be valid. So if you are changing the time derivative of that. So if you are changing B, that means you are creating an electric field. Well, what is the electric field created? So, first of all, are you convinced that, you see, if we talk about previous cases, now here, the source of EMF was mainly the motion of the rod. So it was easy to understand. Now, here, at least in the first case, the reason of the EMF was that the wire was moving around. It was shrinking. But let's look at this one. The wire is constant, so there's no Lorentz force, there's no magnetic force due to the motion of the wire at least. But still, if B is increasing, there is an EMF. So what creates that EMF? You see, in the previous cases, it was the motion of the wire, which was causing some work to be done on the moving charges. But now, if we change B without moving the wires only, still there is an EMF. But that can only be if there is an electric field in the system. So if we are changing B in this example, what we are actually doing is we are creating an electric field in the system, and that electric field is actually pushing the charges along the wire. Because since V is 0, if you write down the Lorentz force, that creates this EMF. But it cannot be V. It doesn't exist. So the only way out is that there has to be an electric field. So in this case, there is an electric field created. Now let's look at this solenoid. What is the electric field created? Also here. Why do the charges here start moving? The charges are not moving to start with, but then as the magnet passes, they started moving. Why did they move? Well, there are only two forces that the charges can feel, the magnetic force, but if they are not moving, they will not be feeling the magnetic force. The second one is the electric force. So the only way out of this problem is to say that the electric field, they are moving because of the electric field. Well, what creates the electric field? The changing magnetic flux. Or the changing magnetic field is creating the electric field. Now let's look at this problem again, back. Let's calculate the electric field directly. What is the electric field? Well, how do we do? You see, the E we don't know. B is something we know. We are given that B has that form, and I will be the thing that is changing in time. So we can calculate the right-hand side. But the problem will be the left-hand side. Just like in the Gauss law, we had the electric field inside an integral. We cannot use it unless we can take the unknowns out, or unless we can evaluate that integral without knowing the electric field. Well, the same thing over here. First of all, if we want to use this to calculate the electric field, we have to be able to integrate this integral without knowing the explicit form of the electric field. And the first thing we have to do is we have to determine something about the electric field by looking at the symmetries of the problem. Okay, first of all, are there any charges here? Are there any regions where you have point charges? Well, the current is made up of moving charges, but they are both positive and negative, so it's neutral. Since there are no charges around, no free charges around, the electric field cannot start anywhere. It cannot start anywhere, it cannot end anywhere. Secondly, what can we do to my system that doesn't change anything? I can just rotate my system around its axis. It doesn't change anything, so the electric field also shouldn't change. Now, the electric field line that satisfies these properties will be just circles. So this is a possible electric field line. It doesn't change on the rotations. It doesn't start, it doesn't end. So it satisfies my properties. Okay, which direction should we choose? So now I will choose that loop to evaluate this integral. Now I already know that E dot dl is the product of their magnitudes. The electric field should be tangent to that loop everywhere. So what can the magnitude of the electric field depend on? Well, if you use the cylindrical coordinates, there is the z, there is the rho, there is the phi coordinates. Can the electric field magnitude depend on phi? Phi is something that changes under rotations around the axis. Nothing should change, so it cannot depend on phi. Now, can it depend on z? Remember, this solenoid is infinitely long. It just looks the same here, here, here. It's the same. But those points have different z values, so nothing should change as I change the z. So the electric field depends only on rho. And along this loop, rho doesn't change. So now we can evaluate that integral. E dot dl integral around that loop is E of rho dl around the same loop. E of rho is a constant around that loop. And this integral just gives me the circumference, which is 2 pi rho. So now I know the left-hand side. Now let's see, which sense would you like to have the loop, clockwise or counterclockwise? It doesn't change the result. Just choose whichever you like. How many of you want to have the clockwise loop, counterclockwise loop? Okay, counterclockwise loop. So the loop is counterclockwise. Now let's calculate the flux. Well, the B is uniform. It's n times I times mu 0. The area is pi rho squared. Is it positive or negative? Well, you see, if you consider the blue loop, curl your fingers in the direction of the loop. This is the direction of the area vector. This is the direction of the magnetic field. They are pointing in the same direction, so the flux is positive. And now we have the Faraday's law, which states that E rho times 2 pi rho, this should be equal to minus d by dt of n I mu 0 times pi rho squared, or E rho times 2 pi rho is equal to minus n is constant, mu 0 is a constant in time, pi is a constant, they don't change in time, rho doesn't change in time, di by dt. So the electric field is minus, well, the pi's also cancel, n mu over 2 di by dt times rho. So apparently the electric field is not counterclockwise, but the electric field lines go clockwise because of this minus sign over there, if the current is increasing with time. So the electric field increases as a function of rho. Well, let's see. Initially, you have the solenoid, no current is running through it. So then you turn on the current starts running in the counterclockwise sense. It induces an electric field in the clockwise sense. At the position of the current, there is an additional electric field trying to oppose it. And whatever is driving this current has to work against that opposition. It will be harder to push the current. Do you agree? Well, this is sometimes called the back EMF. As we are trying to push the current into a system, the system resists it. Why? Because as you are changing the current, as you are increasing the current, let's say, there is an induced EMF which itself would induce a current on the same loop in the opposite direction. Again, another application of the Lenz rule. If you are there is an electric field induced due to a increase in the current, the electric field will try to oppose that increase in the current. It will try to lower the current.
So the direction of electric field depends on the direction of the current?
The time there, you see, let's look at the final expression. We chose the positive direction to be counterclockwise, the blue loop. And then the electric field, the magnitude, turned out to have this component. What is the sign of this? Well, if this is positive, you say this is positive, this is positive, this is positive, rho is positive. The only thing we don't know is what is the sign of di by dt. If this is positive, due to this minus sign, E rho is negative, meaning that the electric field will be in the opposite sense, not in the counterclockwise sense, but in the clockwise sense. Again, it makes sense if you also use the Lenz rule, because in the counterclockwise loop will resist the current, and hence it will try to prevent the increase in the current. But on the other hand, if this is negative, meaning that the current is decreasing, if this is negative, this is also negative. There is a minus sign over here, so the electric field will be positive. So if that is negative, then the electric field will be in the direction of the current itself. So it will be pushing the current. So the current is decreasing. So this induced electric field will try to push the current. Will try to increase the current if it is decreasing. If it is increasing, the induced EMF will try to decrease it. If it is decreasing, the induced EMF will try to increase it. Now let's see, here in this example at least, I just assume that, let's say, there's no current, there's no wire. Well, we can put the wire, if you like. Let's say we have our solenoid. di by dt is increasing. And inside you put some conductor. So you are increasing the current, let's say, at a given instant. Then the direction of the induced electric field would be clockwise, counterclockwise. We already said that if I is increasing, it will try to resist it, so it should be pushing the current in the opposite. It will try to push the current in the opposite sense. But keep in mind, the electric field is everywhere inside, not just on this wire. The electric field is also over there. This is an electric field line inside my conductor. Okay, first question, how come that we have an electric field inside the conductor? Well, that will be the second thing. You see, we had said that inside the conductor there cannot be an electric field if we are in electrostatics. This is definitely not electrostatics. The current is changing with time. You see, even in the case of moving charges in wires, let's say the system doesn't change in time, but you connect it to a battery, there is a current running through it. That current is running through it because of an electric field created inside the wire. So inside the conductor, you can have electric field if you are not in statics. If there are moving charges, in that case, there is nothing that prevents the electric field inside the conductor. But now we have an electric field inside the conductor, which will cause the charges to move around. So this will induce some currents running through my system. Here inside there was this conductor. You see, this solenoid doesn't touch my conductor. But nevertheless, the changing current will create a changing magnetic field, and the changing magnetic field will induce an electric field which will create a current inside this conductor. So the induced currents will basically run counterclockwise. These are called eddy currents. Well, if it's not such a great conductor inside, if it has a high resistivity, still there is the electric field, there will be the eddy currents created, so it will create a huge amount of heat. Well, that is something you might want to use. You can use that to melt metals, you melt conductors at least. You can easily melt them by using changing currents as well. You see, in this example, I assume di by dt to be positive, but if you use AC, di by dt will be oscillating. Here you will get electric field which will be constantly changing its direction, but that doesn't really matter because the current will be changing direction. But as long as there is a current, there will be heat generated inside this resistor. And if you get a large enough current running through your solenoid, that will heat this up. And it can heat it up to sufficiently high temperatures such that it melts eventually. But sometimes it's not something that you would like to have, those currents. You would like to prevent them. So in that case, what you do is you use what is called laminated conductor. Well, what's the laminated conductor? You see, this is your, let's say, this is your solenoid. Inside you have your conductor, but the conductor is not just one piece. It's just very thin sheets separated by insulators. So inside they are insulated films. How many of you had opened up some adapters like this one? You input 220 volts, the output is just 5 volts, 10 volts, 12 volts. So what did you notice? What was inside? There's some circuitry, and well, there's a transformer essentially. So what's a transformer is you have a metal piece. Well, ideally, you have some winding of wire on the left and on the right. And also on the right. You have many turns. And if you look at this metal over here, it's mainly iron most of the time. It's just made up of thin sheets. It's not a single block. It's just many sheets, one stacked on top of the other one. And in between those sheets, you have insulators so that you prevent the eddy currents. The currents cannot just go around. They are blocked. Now, the reason why iron is used, also if you remember, we had the ring launcher on Monday. So there was this rod. And without the rod, the electric field didn't really, the ring didn't launch high. With the rod, it went much higher. Also, without the rod, there was no light coming from the light bulb. With the rod, there was lots of light coming from it. Now, the reason is the iron is actually itself a magnet, in a sense. In the sense that if you look at the iron very closely, very small parts of iron, you can imagine iron as just a collection of very small magnets. But since all those magnets are randomly aligned, you don't get any magnetic attraction or repulsion. But that's also why other magnets can attract or push. Other magnets will attract that magnet because it itself is made up of many, many very small magnets. Now, if you put that iron in a magnetic field, those very small magnets making the iron itself, they get aligned to some extent. So the iron itself, first there is the magnetic field that you apply. Second, there is the magnetic field created due to these alignments of these very small magnets in the iron core. So you get a huge magnetic field, even if without the magnet you get a small one. Without the iron you get a small one. With the iron you will get a huge magnetic field. The factor can be as large as 10 to the power 4. Not a very small effect, it's a significant effect. If the magnetic field becomes very large, but at the same time it just changes direction, the frequency doesn't change. So the rate of change of the magnetic field becomes huge. So that is why when we put the iron core, the magnitude of the magnetic field became huge, but its frequency didn't change, and hence the rate of change of magnetic field become huge. So that's why we had to put the iron core. Here, the effect of this iron would be mainly when you put the iron, you see, if you have such a small solenoid, what happens is the magnetic field lines, they are just spread out. Some of them will go through this solenoid over here, but most of them will just spread out. What iron does is it traps the magnetic field lines. So if you send the current, let's say through this one in this direction, well, this creates a magnetic field in which direction? Inside. It will be upward. And these magnetic field lines, they go around this iron. They don't go out. So whatever flux you create over here, you also create over here. Well, let's see. Let's assume that here on the left-hand side, on the right-hand side, you have NP number of turns. This is called the primary, because that is where you send the current. There are NP turns over there. And here there are NS turns. There are NS turns on the other side. Use the ratio of the fluxes, the flux passing through primary to the flux passing through the secondary. You see the flux will be just the flux of one ring multiplied by the number of turns, both here and there. Each ring on the left or on the right, they have the same flux. So the flux will be basically proportional to the number of turns you have on the left and on the right. So the ratio of the fluxes will be NP divided by NS. Now, if you send some EMF source, the potential across the primary would be just minus d phi primary divided by dt, which is nothing but the Ampere's law. In the secondary, well, it's basically the same. Well, of course, if, let's say, here you use a direct current source, a DC source, well, this derivative will be 0. No, sorry, that is Vs. If you send the DC source, Vs will be, no, this will be 0. That the flux will be constant, so that derivative will be 0. The flux are constant, nothing will happen. You just send some current on the right. But if you use an alternating current, for an alternating current, the time derivative is just proportional to the current itself. And remember, the flux is proportional to the magnetic field times area, and the magnetic field is proportional to the current. So if the derivative of the current is proportional to the current, then the derivative of the flux will be proportional to the flux. Or let's say, even without that, let's say Vp is minus d phi p by dt, which is minus d by dt. Phi p is phi s np by ns. I just use that relation over there, the relation between the fluxes. Well, np and ns, they are just constants. Vp is equal to minus d phi s by dt multiplied by np over ns. But this is nothing but Vs. So Vp over Vs is equal to np over ns. Of course, this is valid only if you use the alternating current. This is not valid for a DC current. Now, what does this tell me? Suppose for some reason, well, you have some initial potential, you want to change that potential to some other value. What you might be interested in, maybe you have the initial potential is 100 volts, but you want to have 1000 volts. Well, so you want this ratio to be 10. Well, you just make a transformer whose number of turns, the ratio of the turns is 10. Or if you want to reduce the current by a factor of 10, again, just use the same transformer. You can just increase, step up, or step down the voltage, depending on your needs. Now the question is, why would you like to increase the current to tens of thousands, tens of volts, or reduce it from tens of thousands of volts?
Do we have all that transformer in the reactor?
You should. Probably you already have it. You see, what you would like to do is you would like to get a low potential. So there are a couple of means of doing it. One mean is using a transformer. The other means would be to use a resistor. 220. 200. Step up or step down? Probably step down. You see, Turkey, we have 240. Okay, so you want a step down transformer. You want to step down 240 volts to 110 volts. So that's why you want a step down transformer. Yes, any other questions? Okay, see you on Monday.